And instead of, let's say, a mere star in the middle, he has a Madonna and Child. And this was said to have crossed the Atlantic and come back and was preserved to this day. This is also gimbaled. You can see it's in a container so that with the opposite pegs it will not be disturbed so much by the motion of a ship. The problem with compasses, though, is in variation, in that much of the world has magnetic anomalies, so that depending on where you are, the compass does not point true north or south. And also, you know that the magnetic North Pole and South Pole are not at the geographic poles, and they tend to move over time. So currently, the North Pole magnetic is up in northern Canada, and the South Pole is on one side of Antarctica, quite far away from the true north and true south. So in the equatorial zones, in this map that was Sir Edmund Halley first drew for variations around the world, you can see that in tropical zones you only have variation of 10, maybe 20 degrees east or west as you go around. But if you come down to where we are, we actually, if you saw that chart I brought out, the magnetic variation on the south coast of Australia is very little, because the south magnetic pole is due south of Australia. But if you go over here, it's 40 degrees east variation. And similarly, as you go into the North Atlantic or the Bering Sea, your magnetic compass is almost worthless, because the pole will suddenly be south of you or due east or west of you as you're heading further north. In the polar regions, you use what's called a sun compass, which sights the sun and gives a more true bearing of your direction. Here's an old armillary, which is in the National Maritime Museum in Greenwich, England, which was used by Halley and others to determine the difference between the magnetic compass and the true north-south. So these are sighting astronomical instruments to be compared to the magnetic compass. In Europe, and especially England at this time, the development of these precision instruments were invaluable to the growth of the navies and the merchant fleets that went around the world. And this was the prized possession of any ship. What was called the soul of a ship is its compass and its other sighting instruments. Here's a pocket watch compass sighting device with tables, all in one handy packet, that is in a museum again in England. And then they would have the major trouble, though, was I mentioned the determination of longitude was very difficult, because it depended on all kinds of celestial calculations, when that was a very complicated mathematical problem. So most ships went out using deduced reckoning, or we call it dead reckoning, especially if you don't get it right. And they would measure time by an hourglass, and they would try to determine just by estimation how far they went, how fast, etc. But an hourglass is a very inaccurate instrument at sea. And so it waited till the development of this instrument by the clockmaker John Harrison, who developed a non-pendulum clock that could, by spring action, keep an accurate time for months on end. And so this was his first chronometer, it was called, and he applied this to the great competition for the determination of longitude, which went on for decades to try to find a better way to measure longitude at sea, and essentially came down to this timekeeping. And this was the later fourth version of his chronometer, which became the watch that Captain Cook took out to test, and then it subsequently became the way to determine longitude. We keep Greenwich Mean Time, and then we measure our local time by sighting the noon sun and compare that to the chronometer and the time back at Greenwich as the standard now. And thereby you could determine how far you are around the world fairly precisely, and that's what we've been using up till recently. Here is that observatory in Greenwich where this is the time ball that I mentioned, which would be dropped right at noon at Greenwich, and all the ships down on the Thames would set their chronometers to that, and they had to watch the ball and not drop the ball or be on the ball and measure their clocks, set them, and then go out around the world. The Harrison chronometer would only lose maybe half a minute over a year. It was a very accurate clock. Of course, now you can get a watch for almost nothing that is even more accurate. But this all added up to the tools of navigation, which were familiar, the compass being essential, and then the sextant sighting device, the watch or the chronometer, and then all of the books and tables that help you determine these matters. The Nautical Almanac is published every year with all of the predictable heavenly bodies, motions, and other facts that you use numbers to determine by celestial navigation where you are. A star finder so you can sight the proper heavenly body that you're looking for. Then you have your paperwork, your charts, your parallel protractor, and now you have celestial navigation calculators that have the functions built in so you can quickly determine the outcome of your exercise of navigation. And so here is what is our standard tool now, the sextant, and I do have this one up here, and I'll show it to you a bit later. This is a very valuable instrument on board, and I'm not sure what they're doing on the bridge without it right now, except that we're on just a straight course. They take sightings as exercise and legally must have it on board, and all licensed officers must be trained and examined in the use of it, but it is a backup to all of our modern systems. So you have a sighting device that will go to a mirror, and the view of the sun or other stars or the moon will come down off the mirror through filters so you don't burn your eye out, and then by the axis arm it will move, and when you can see the horizon matched with your heavenly body, then you get an angle determination, which is on the index arm. So here's a mariner out there doing this, and you usually will do this for noon sighting to get the sun, to get your latitude indication, and then you'll do it at dusk as particularly planets are visible and the first rising stars in the evening come up, and that's the other time that the sightings are generally taken. So as you look from your vessel off, you'll have a horizon, and then you'll match this in the mirror with some variation depending on the style of the mirror, and then you'll rock your star, it's called, where it will you'll bring it down and it will vary, and then you find it directly perpendicular to the horizon, and then you can get your reading. Now then you'll take that reading, which is an angle declination reading, and you'll take it and convert it to time reading, because the Earth is divided by its circumference into essentially a large clock, 360 degrees around, 24 hours, can be broken down into minutes and seconds. And so distance is actually the same as time, so that 1 minute of longitude at the equator is equal to 60 miles, and 10 degrees is 600 miles. And so time and distance become an equation that is then put into the Nautical Almanac, and then you measure this, convert it, and get a time distance reading, and thereby go through all of these tables that are determined according to where you are, when you are, and you will be able to hone down mathematically your position. So you have a sheet like this where you've sighted a 65-degree call of the sextant height, HS, and then you'll put in some variations of where you're measuring it in your mirror. That's called the index correction. And then you add a height, which is how high you are above the sea level. So in a small vessel, you're only maybe 5 to 10 feet, but if you're on a large ship and you're 100 feet up, you have a different variation of your mathematics by your height. And then you'll have what's called a D value will come in. And there's some variations of, for instance, just the fact that the Earth is not completely round and the year is not completely exactly 365 days, just like we are not exactly 24 hours. So there's some variations like that that are common to having a leap year or other corrections. And then you end up with a zenith distance. Then you look up in your almanac your date and your Greenwich Mean Time, and then you'll calculate that down to finally getting your latitude. Here we are at 44, 2.5 north. You generally will always be carrying a general dead reckoning view where you were yesterday, where you think you're going, and approximately where you are. So in this exercise, if you get something that's really very different from where you approximately are, you know you did your math wrong, and that then you have to go up and do the whole thing over again. Typically on a ship you'd have two people doing the exercise. You'd have someone doing the sighting and calling out the numbers, and then someone writing that down, and then it goes through the calculation, and you end up with a number of different ways to determine your longitude. So you have what's called, you'll get a line of position viewing the sun or another star or a planet, and then you'll take a view of it, a couple of lines of positions, and then you'll take a perpendicular from that and you'll get a fix, which will be your approximate position on your chart. Now this is the exercise that all cadets must go through, so that here in this plotting chart you have sightings of the moon and the sun, and this would be Mars. And again, you're going to take lines of position, a perpendicular, and that means you're about right there, which then you take to your chart. You're 34.8 north and 50.9 to the west, and you'll get your general precision honed down to where that will be good enough. You'll have to then, when you come toward land, be watching out for your landfall, so that you may be within a mile or two with good, let's say, hand navigation, but you still better keep a lookout, because if you have an error of a mile or two, that may be enough to wreck your vessel. One thing you'll also carry is a star finder, which nowadays is a plastic circular device with all of the heavenly bodies on it, and then this blue area is actually your seasonal view, and you'll put a different overlay every month that will then give you, well, that's your zenith now. In the winter, your zenith may be over here. And then these are the celestial longitude and latitude, which you can say, oh, well, Riga is over here, and for instance, this next chart, we have Jupiter is now crossing the heaven, and there'll be a sighting here. And then this can be put into this latitude and longitude of viewing the heaven, so that you know where it's going to be the next night. Once you're used to this, you look up there, well, that's what I saw last night. That's the same one. We'll shoot it again, and then we'll get our calculation from that. We will use these basic 32 stars to sight. So depending on where you are in the globe, you can see some of them better than others. Here again is Orion's belt is almost due east, sets due west. And we're used to Pleiades and Vega and Cassiopeia and the Polaris and the Big Dipper and the Small Dipper. And as we come down here, we get the crux is actually the Southern Cross, and then you have Scorpion, Antares, and others that you don't usually see if you're in the far northern latitudes. And so this is where you combine the ones that are most convenient. You usually pick out 3 of them and cite them to get your calculation, though the moon and the sun, of course, are the easier ones to always know where they are and always be able to follow them crossing. So I move on to the modern era with this cartoon, which if you can't see it there, it says, "Hey, my friend, isn't it not best to learn the traditional methods of celestial navigation before starting with that calculator?" Of course, that calculator may have actually been an abacus. I'm not too sure. But to this day, the Maritime Academies still require exercise and training in this somewhat cumbersome process. But the problem with the recent era is that with these flying boats that are up in the air, have you ever taken one of those? Those go so fast, it's very hard to determine your navigation looking out a tiny little window of an airplane as the heavens go by. And so when it came to air navigation, it became very difficult. First of all, you didn't have a sea as a horizon, so you had to have an artificial horizon, and then you had to do very quick calculations, and often we're looking down out of the plane to see where land is to confirm your navigational fix, which was 100 miles back. So for aviation, these techniques became very cumbersome, and that impelled the development of new techniques, primarily radio location beams. Under the sea, there are low-frequency beams that help submarines find their location in the ocean. And then this led to the current era of GPS, or the Global Positioning System. And this was developed primarily for aviation and also missilery. And I met a gentleman who was on the program at the Pentagon at its initiation, and they said that they had a very serious problem. They had missiles in submarines that were going to be fired, but they didn't know quite exactly where they would come out of the water or where they were going. And in traditional artillery, you'd use some paper calculations and you'd sort of see the effect of your estimations. But in the new era of rocketry, this was such a problem that then it was decided to put up the entire array of satellites that give off a very distinctive beacon frequency that then is taken down into a device and is triangulated just like a celestial fix, as I described, but instead from these satellites that are in geosynchronous orbit, and there's at any given time in your GPS even the one in your car now, they will monitor 5 or 6 satellites, and then they will give an instantaneous calculation and a very close determination of where you are, now down to about a meter. Now, it used to be that when the Pentagon developed this, this was top secret, but the word of it was out eventually, and it was about 15 years ago that an act of Congress required the Pentagon to distribute the technology to be allowed for transportation, and now it's become a very common tool all around the world. I hear they now even sell wedding rings with GPS locators in them, but I don't have mine on right now. The problem with this GPS system, though, is that it is still held as a security system by the United States, and this has been criticized by the international community, saying this is now much too important to be left to a military organization, since so many ships at sea and airplanes now use it, and it should be not just given over to the civilian, but there should be a global management of this new navigational technique. So thereby the European community, along with India and China and the UK, have sponsored what's called the Galileo Project to set up their own system of satellites and receivers and have a competitive or an alternative to the GPS system in case for some reason that's turned off. They have had a beginning of the project has yet to become operational, but it may mean that soon you might have to go out and buy a whole other set of equipment if you want to have an alternative. Meanwhile, the GPS is now a gift to the world thanks to certain taxpayers, and it is very essential to ships like this who will have a GPS location running at all time. You can see it on your Channel 3, and it will give you a fix that will be so accurate as to the ship will be able to come right up to a shore and with a computerized waypoints enter toward a harbor. Now, as we go into a place like, and we were in Albany yesterday, in that narrow gap, a ship will not use a computer and a satellite to go through that. They will be steering by eye and sight and pilotage at a certain closeness to shore. But otherwise, the GPS means that you can travel almost anywhere in the world without navigational error. And so does this mean that celestial navigation is so antique and ancient that it's not necessary anymore? Well, where it is now being used all the more is outside of our little planet, and out where either the space shuttle or other planetary probes will navigate by doing the exact same thing. They will fix upon a heavenly body, and now in 3 dimensions, not just a panoply overhead, but they'll have them in all directions, and then they will be able to take a very precise course so that these great space shots that go around Jupiter and off to other planets or out of our solar system are determined by celestial navigation done by a computer. Now, this is one of the vessels that I sail in off my little islands in New York, and so we go out and practice our traditional techniques. This is a vessel with no GPS, no winches. We do bring along an engine in case we want to get home, but if you're ever in that part of the world, you can come out and we'll show you how we can find our way using celestial navigation, and we're not sure if we'll always get back, but we'll have a good time getting there anyway. So that I leave you with this illustration from the North Sea and the assurance with all these techniques, both ancient and modern, you can get there from here. And I wish you all a great voyage on this great ship, and hope that your navigation is always true. And now I'll show you the Sextant. Anybody want to come up and see it? We will, for the lack of the right stars here, we're going to be sighting the exit signs because they're seen more clearly on the Sextant. But essentially, you can come up and check this out, which is the sighting device, the mirror, the split mirror in this case. These are the filters, which we don't need indoors. And then the index arm, which will then bring whatever is above to the horizon. In this case, I'm sighting the balcony's exit sign and bringing it down to the lower level, and then I can tell that, oh yes, you can see it quite clearly, lunch is being served. But if you want to come try this out, I'll show it to you down here. Thank you very much. My pleasure to sail with you.